Welcome back. In the second lecture, we'll cover the fluid flow phenomena. The learning objectives are appreciating the wide variety of fluid flow phenomena and to discuss the unique role that the Reynolds number play in fluid mechanics. One of the more serious hurdles in analyzing the flow of a fluid is the bewildering range of phenomena which may occur in seemingly simple flow situations, and how at times very small changes in flow parameters produce drastic change in flow behavior. Consider the flow coming out of a faucet. When the flow speed is less, the fluid comes out or the water comes out as a smooth flow. But if you increase the speed, the water comes out as turbulent with a lot of swirling around within the stream. This clearly illustrates that two different flow regimes are operating in two different flows. And quite clearly, the two flows cannot be analyzed with the same basic principles. One of the first experiments connected with the varieties of flows was conducted by Professor Reynolds of England in 1880. In this experiment, he had a water tank and a pipe with a smooth entrance. The pipe was submerged in water for some length, and then there was a valve that controlled the flow. Ink was injected at the center line of the tube of the pipe, and the flow of this was observed. These sketches are from the original paper by Reynolds, in which they show that when the flow speed is very low, the streak of ink introduced at the center of the tube comes out smoothly and flows down the tube. But when we increase the flow speed a little bit, the ink spreads out downstream in the tube. At still higher Reynolds number, at still higher velocities, the streak of the ink is disturbed significantly, and a phenomena known as turbulence is set up. These pictures of the flow are more recent experiments, and we can see clearly in the first picture the streak is straight line. In the second picture it starts getting some waviness. In the third picture there's a lot of disturbance and the ink is spread out across the cross section of the tube. By the fourth one it is completely broken down. Reynolds explained it by saying that as the flow speed increases, turbulence is set in. The flow is said to be laminar to begin with. In laminar flows, the layers of fluid appear to be sliding over each other smoothly, while in the turbulent flow, there is a lot of mixing transfers to the flow. Reynolds also established that this transition from laminar to turbulent occurs not at a flow speed, but at a composite parameter depending upon the viscosity, the density, the velocity, and the diameter of the pipe. When a combination of these parameters defined as density times the velocity times the diameter of the pipe divided by the viscosity, this parameter exceeds certain value, the flow becomes turbulent. So, if the diameter of the pipe is more, to get the same value of the parameter, you need more velocity of the flow for the turbulence to be set in. The following series of pictures shows flows past a cylinder. The flow is made visible by various devices. In this picture, the flow is made visible by sprinkling a powder on the surface of the water flowing past a cylinder and taking a small time exposure photograph. At a very low speed of fluid, for water, a speed as low as 1.60 10 to the minus 6 meters per second, that is 1.6 micrometers per second, when the cylinder diameter is 10 centimeters, the flow is symmetrical. You would notice there is very little asymmetry in the flow, left, forward and backward. As we increase the flow velocity, and for water, the speed comes to now 15 micrometers per second. For air, that would be 150 micrometers per second. On a cylinder of diameter 10 centimeters, you can see a marked asymmetry in the flow. Now the flow is from left to right. There is a stretching of the flow towards the right. This asymmetry is a common phenomenon. As we increase the flow speed by another factor of 10, you could see the asymmetry more pronounced. Not only asymmetry, we say beginning of vortices behind the cylinder. Two vortices, one on the top around here and one there, in which the fluid seems to be swirling around. In fact, a dead water region develops. The fluid from this region does not leave this. The flow coming in from here goes around and passes by, leaving this flow to be stagnant there. A still higher speed, we can see these vortices very clearly. This picture has been taken in water with the cylinder surface coated with a layer of condensed milk. As the water flows, the condensed milk dissolves slowly and is seen in this picture in white light. The flow there leaves the surface, goes around and swirls back. Similarly, here, these are termed as attached vortices. As the flow speed increases further, a beautiful picture emerges. These vortices that were attached in the previous picture now are shed from the cylinder one at a time. First at the top, then at the bottom, then at the top, then at the bottom, with a marked regularity. These vortices grow in size as they travel downstream. The resulting picture has been named the von Karman vortex street after a German scientist, von Karman, who studied this. This is a very common phenomena. The pattern like this is seen behind sand dunes in desert, behind rocks jetting out of slow flowing streams. If we measure the velocities in the wake of the cylinder, behind the cylinder, through a device which is known as a hot wire anemometer. This consists of two electrodes across which a very thin wire is stretched. This wire is heated with an electric current. As the flow takes place over this wire, the wire loses heat, and if we can measure the amount of heat that is lost, we can estimate at what velocity the air must be crossing the wire. This probe, being very small in diameter, has a very small time constant, and from using this we can measure the fluctuations in velocity. We've shown here a few signals at the various Reynolds number. You see, the Reynolds number is the parameter that we discussed in the Reynolds experiment. The density times the velocity times the diameter divided by viscosity. When the Reynolds number is about 100, you get almost a sinusoidal signal from the hot wire probe. This represents that the vortex are shed with a fixed frequency very regularly. As the Reynolds number increases, the first thing to notice is that this frequency increases. Second, the regularity breaks down till at Reynolds number of 600, the regularity completely disappears and we get what appears like a random fluctuation of signals. This is the turbulent flow. We again go back to our cylinder at a Reynolds number of about 2000, which for a cylinder diameter of 10 centimeter translates to water velocity of 0.02 meters per second, 2 centimeters per second, or in air about 20 centimeters per second. We get a turbulent wake. In the wake, you can see turbulence. If we increase the Reynolds number further to 10,000, you can see the turbulent wake very clearly. You would appreciate how far we have come up from the first picture we showed, where the flow ahead of the cylinder and behind the cylinder were almost similar looking. Here, there is no symmetry fore and aft. It's still higher. Reynolds number, that is, when the velocity in water is 1 meters per second, you see a layer that travels around the cylindrical surface in the top picture, and it separates from the top surface at a point nearly here. We say a boundary layer has developed on the cylinder. A boundary layer, we will discuss later on in the course, is a thin layer in which the viscous effects of the flow are confined. We will have occasion to discuss this in great details later on in the course. But for the moment, you assume that outside this thin layer, which is shown with white smoke in this flow about a cylindrical surface, all the variations of velocity are confined within this region. Outside this region, the flow is non-viscous. In the picture below, when the water velocity is increased 5 times, or the Reynolds number increased 5 times, you see this boundary layer is now turbulent. And the separation is delayed. Separation is somewhere here, or maybe even here. The boundary layer is thickening, but it's separating at about the second location that we shown. In turbulent boundary layers, then, the boundary layers separate from the body. What happens after the boundary layer separates? As you see in both the pictures, the smoke has now penetrated in more parts of the flow field. We have this picture here in which we have a sphere rather than a cylinder, like a ball. there's smoke injected at the leading point of this thing at about here, and the flow is taking place from left to right. And for a Reynolds number of 15,000, we see that the flow separates at about this point, slightly before the highest point. This results in a wide wake where the smoke is being distributed. This large-scale disturbance results in large drag on the sphere. However, if we increase the Reynolds number to about 30,000, the flow separates at about this point, much further down the spherical surface. And the extent of the wake is narrower. We will see later on in the course that a narrower wake indicates that the drag on the body is far less. In this picture, we have plotted velocity versus drag starting from very low velocities. At very low velocities, so low that the Reynolds number is less than 1, we see that the drag is linearly proportional to velocity. This is the regime of flow that you studied in your high school. You had studied the formula, Stokes formula. The drag is 6 mu Vd. This 6 mu Vd is applicable only in this very narrow range of Reynolds number less than 1. Typically, that would mean that for a fluid like water, the velocities would be in micrometers per second, and the dimensions of the bodies would also be that low. Only very fine dust particles, microbes, and such biological entities have a Reynolds number as low as that while moving. The water droplets in clouds, when they are very small, of the order of micrometer size, also have Reynolds number which are very low. So it is for very small microscopic world that we can use the Stokes formula, drag is equal to 6 mu Vd. As the Reynolds number increases, that is the velocity increases, the drag deviates from that straight line, and at larger speeds, the drag curve is like this. Notice that this is a parabolic curve. But we see a strange phenomena. As the velocity increases, the drag increases parabolically, like velocity square. But then at certain velocity, actually certain Reynolds number, there is sudden decrease in drag. And then drag increases again with a relation which is parabolic again, but with much lesser coefficient. You see, it is only after the velocity increase to the right edge of the blue rectangle that the drag has caught up with the drag which was at the left edge of the blue rectangle. So in all this region, the drag is less than what was at the left edge of the blue rectangle. What is happening? Simple. At lower velocities, the flow is the boundary layer flow is laminar, but at the larger velocities, the boundary layer flow is turbulent. Like we saw, the laminar flow, the wake is wider, so drag is proportionately higher. But when the velocity is larger, that is the Reynolds number is larger, the wake is narrower, the separation of the boundary layer, which is turbulent now, is much delayed. The wake is narrower and the drag is lower. We'll see later on in the course that the pressure distribution around the sphere changes drastically in the two regimes, the laminar and the turbulent. Another interesting thing to note is what is called streamlined versus bluff bodies. In a streamlined body with a rounded nose and a long tapering tail, like the cross-section of an aircraft wing, which is termed as an aerofoil, the flow is smooth, there is very little separation, and there is a very narrow wake. This flow has been visualized in a wind tunnel using smoke as the tracer particles. In the lower picture, we have a cylinder which does not have a long tapering tail. It is a bluff body, and in this we get a large wake, a highly disturbed flow. In the first case of the streamlined body, the pressure is at the front, which is pushing it, recovers at the back, and the pressure is pushing it forward from the back. And so these pressure differences cancel out and we have low drag. In the second case, the pressures in the front of the body are much larger than pressures at the back. And so there is a large drag. Drag of a streamlined body is an order of magnitude lower. This slide illustrates that. If we take a rectangular body of thickness T and we have flow past this, we have 4 cases here. In all 4 cases, the velocity is the same, fluid is the same. In the first picture with the rectangular body, the flow separates right at the nose in these regions. It results in a large wake and with a drag which is F. In the next case, we have just rounded the nose. And we rounded the nose, the flow does not separate at the edge like in this case. So the wake is narrower and the drag is about half of what it was in the first case. In the third case, in addition to having a rounded nose, we have attached a long tapering tail. Because of this, the wake is still narrower and we get a drag which is less than 1/10 of the drag in the first case. In the fourth picture, I've compared the drag on a circular cylinder of the frontal diameter, only 10% of the frontal diameter of the long tapered tail body on the left, and they have the same drag. So a cylindrical wire that small, 1/10 of the size, has the same drag as the tapered streamlined body of the picture on the left. Remarkable. In fact, you would have noticed that when the aircrafts were first invented, they used biplanes which were strung with a lot of cables. Those cables contributed to a lot of drag, even though those cables were very thin. In fact, later on, they started replacing these cables with cables which were with aerofoil shaped, or which had a cross section like this, so that the drag could be reduced. In fact, the aerodynamic drag of the spokes of a bicycle wheel is quite substantial. Those spokes are cutting through air, circular cross section, and so add a lot of drag because there are a lot of spokes moving at the same time. On the top is a NACA 8410 aerofoil used in many early aircrafts. The nature evolved itself in such a manner that the dolphins have a shape which is quite like that of a NACA 8410 aerofoil. It is because dolphins like to swim through water, and having lower drag would give them advantage. In fact, if you look at high performance cars, they have streamlined shapes which do not have protrusions which add to drag. There are no sharp corners. They appear to be smoothly flowing. This graph shows the evolution of the cars from 1920 to year 2000. And we see how the shape of the cars changed and how the drag coefficient is a non-dimensional number that indicates how much drag is. It is given by drag divided by velocity square and the frontal area and the density. So related to drag, more the drag coefficient, more is the drag. And you see how the drag coefficient is decreasing. In fact, the drag coefficient of some modern day cars are so low. Nature also does wonderful things. Large sea anemones, which are predatory animals that live on the bottom of the sea. They catch small marine life in their tentacles, but when the water is flowing, they are not rigidly attached to the floor, so they are very sensitive to the drag of water which is moving. The shape is steadied. We have seen that at low speed, an anemone looks like this with a CD of 0.9. As the speed increases, the fibrous tentacles divide themselves into groups, making small pods, so that the flow could pass through them, and the CD decreases drastically to 0.4 based on the same area. At still larger speed, they narrow down, reducing the drag coefficient further to 0.3. And still larger speed, they completely turn themselves in and the drag coefficient decreases. These have been taken from a very interesting book, Life in a Moving Fluid, whose reference is given here, I would recommend this highly. More on the drag on trees. The trees standing in a wind, the canopy of the tree offers a large drag. Because of large drag, the tree tends to topple over. The drag, there is a pivot point about which the drag would tend to topple over. Of course, the weight of the tree acting from the center of gravity would like to keep it straight, but for large trees, this drag could be substantial. The drag is because of individual leaves. There is no bulk canopy, individual leaves. Scientists have studied, and they say the shape of the leaves changes. For a tulip or a yellow poplar tree, you see as you go from top to bottom, the leaf folds over and offers lesser area to the flow. And if it offers lesser area, that means it reduces the drag. The black locust leaves, as the wind blows, they close up, offering lesser resistance. This also has been taken from the book of Vogel, Life in a Moving Fluid. The book contains a lot of other examples of how the moving fluids affect the life of the organisms living in water. I think it should be clear to you by now that the fluid flow phenomena changes as the Reynolds number changes, and unless we have a clear understanding of what kind of flow is taking place, we cannot model it properly. That's why we have analyzed or presented to you these different phenomena right in the beginning of the course, so that you are familiar with the terminology and could visualize what is happening. Now we will discuss the flow inside a tube, called a pipe flow or internal flow. Let's consider a circular pipe. As a fluid enters the pipe, let's assume it has a uniform velocity across the section of the pipe. Now we understood viscosity, and we have studied the no-slip condition at the wall. We mentioned in the last lecture that any fluid adjacent to a solid wall does not slip at the wall. It has the same speed as the wall speed. So if the wall is stationary, the fluid exactly adjacent to the wall would be stationary, would have zero velocity. This fluid which entered this pipe at a uniform velocity would see an immediate stop to a layer of fluid in immediate vicinity of the pipe wall, and so after a little time the velocity profile would look like this. The effect of viscosity has penetrated up to this depth from both walls. At a little further distance, this penetration would be further down, more, till all the fluid in the pipe is affected by the viscosity. This penetration of the viscous effect is the same thing that we discussed in the last lecture, the diffusion of vorticity. This ultimately, in this pipe, we will develop a parabolic velocity profile that you studied in high school. Notice one thing, the velocity at the center, which is maximum, is increasing as you go from left to right. Why? Because same amount of fluid must be flowing across each section. And since in the later sections more of the fluid is slowed down, so the fluid at the center must have speeded up. In fact, you would study later on that the maximum velocity at the center is twice the velocity of the flow at the entrance of the pipe. In this picture, the shaded area is the area that has been affected by viscosity. The remaining area is unaffected area. It's called the core area. After this length, the velocity profile does not change. And we say that the flow is fully developed. It is between this and this that the velocity profile changes. We call this a developing length, an entrance length of the pipe, where the flow is developing. Developing flow, and then fully developed flow after the velocity profile has once become parabolic and the viscous flow covers the whole region. How long is this developing flow region? The calculations were shown that this is proportional to the diameter of the pipe and to the Reynolds number. For laminar flow, this length could be quite a bit. This length could be up to 100 diameters in laminar flow. But in turbulent flows, this length is quite low. We will discuss this too later. Here we are comparing the flow profiles in the laminar flow and the turbulent flows. In laminar flows, the maximum velocity is much larger than the average velocity. Not so in turbulent flow. In turbulent flow, the central region is quite flat. The gradient of velocity at the wall is much larger in the case of turbulent flow than in the case of laminar flow. Since the shear stresses are related to velocity gradient, so shear stress on the wall in turbulent flow is much more than the shear stress in laminar flow for the same mean velocity. Much larger shear stress on the wall has much larger pressure drops, much shorter developing lengths in turbulent flows, as we discussed earlier. Most pipe flows are turbulent. In fact, we would later on learn that the pumping cost when the flow is turbulent is most economical. We'll discuss that issue later on. Water flowing in a 10 centimeter diameter tube, which is about 4 inches diameter, at 20 centimeters per second is likely to be turbulent. Most flows in the pipes are turbulent. There is another property of turbulent flow that we want to discuss, or internal flows, sorry. There is another property of internal flows that we want to discuss. Consider the first picture. Here we have flow in a converging diverging pipe. The length of the converging portion is much smaller than length of the diverging portion. Let's assume The fluid is water, an incompressible fluid. As the flow enters from the left, the velocity of the flow must increase, because if we are passing the same flow, as the cross-sectional area decreases up to the throat, the velocity must increase. The yellow line shows the variation of velocity. Then in the diverging portion, the velocity decreases again. What happens to pressure? As the velocity increases, the pressure decreases. In accordance with the Bernoulli theorem that is you studied in high school, and which we will cover here in much more details in a later chapter. The pressure increases as the velocity decreases, and then the pressure increases again after the throat as the velocity decreases. But if the length of the diverging section is reduced, like in the lower picture, you see very interesting thing. The flow here separates at the throat and comes out as a jet. And if it comes out as a jet, the velocity does not decrease. So while in the converging portion the velocity is increasing, the yellow line, in the diverging portion the velocity does not decrease. And because of this, the pressure does not recover. Pressure does not increase. And so there is a decrease in pressure down this short nozzle. And this results in loss of energy. We have to be very careful about the diverging portions, because the flow tends to separate. I end this lecture with a description of two pipe fittings. One is in which there is sudden increase in the cross section of the pipe, sudden expansion of the pipe. The flow tends to expand, but the flow separates at this region, developing an annular dead water region. The fluid in this region does not move forward, it is just recirculating there. The velocity decreases like this, but because of losses, the pressure does not change very much. Since the velocity is decreased, if there was no flow separation, the pressure would have increased, but the pressure does not increase. This means there is a pressure drop at a sudden expansion. And if we are pumping water, that would mean we have to apply more pressure difference, we have to expend more power in pushing the water through this sudden expansion. Similarly, in a sudden contraction, because the flow is slowing down here, there is a separation. Here, there is an annular vortex here. Then at the sharp corner, there is separation again. The fluid cannot turn sharply, and so we have an annular vortex sitting right there. All this results in head losses. This is the minimum cross section of the flow. It's called vena contracta in fluid mechanics. Pressure decreases because the velocity increases. Thank you very much.